Okay, thank you. Yeah, so let me start with some very kind of personal motivation of studying property testing. So we have a lot of very large graphs all around, things like the web graphs, social networks, but also if you think about the human brain, the connectivity of the neurons, that's a very large graph. And all these graphs are very big. Their sizes have billions of nodes. And if you also look at additional information, this sometimes amounts to petabytes of data. And from a and it's a very interesting challenge to understand the structure of these very large networks, to understand things like connectivity, whether they have small cuts, whether they are clusterable, and so on. And often the challenge is that these graphs, these networks are very large. They may even not fit into main memory. Even if they do, often computing such things like cuts, clusterings, and so on requires a lot of running time. And this motivates for algorithms that also are very fast and are trying to obtain this information by random sampling. And in particular, if you think about social networks, for example, these networks may contain valuable information. One example question I'm always giving is the question whether you can decide by looking at the social network of a whole country, whether this country is a democracy or a totalitarian country. If you want to do this using tools, say from machine learning, the issue is that each of these graphs is very big. You need to look at the number of these graphs to get sufficient information to be able to decide such a question. And so you have to deal with really large inputs. On the other hand, I think this question is in practice not very hard to solve, because in a totalitarian country, typically, you don't have social networks, so you just have to distinguish an empty graph from a non-empty graph. Yeah, you get the idea behind it. Another potential application is to look at software, at function calls in software, which is sometimes done to identify malicious softwares. And also there you have graphs and you want to identify information, you want to understand the structure of the network to identify viruses and so on. And also that's even more of a potential application, because we currently don't have access to the structure of the human brain. But potentially you can assume that at some point we will be able to get to maybe also get this information from, I don't know, some kind of how's it called? Yeah, some kind of medical process, and then one could try to understand whether the structure of the human brain shows some special structure in the connectivity of the neurons, which could also indicate that the patient is ill. Yeah, so all these applications have in common that we need to obtain a lot of information from very large networks. Often, if we want to think of this as machine learning applications, we need to not only understand a single network, but many of them. And for this purpose, we need to have very fast algorithms that obtain information from graphs. And yeah, my personal point of view is that graph property testing provides a theoretical framework that allows us to understand or to study such questions about graphs. So it's yeah, it was introduced by Rubinfeld and Sudan and graph property testing by Goldwasser and Ron. And it provides a formal framework to study sampling algorithms. So this can be used to obtain a better understanding of the possibilities and limitations of random sampling from very large networks. It can be used to design new algorithmic paradigms, and we usually follow an approach that is driven by complexity theory. We want to understand what classes of properties can be tested in sublinear time. And one way to phrase such a question is to say, what can we learn from the local structure of a very large object, in this case of a very large graph, about its global structure? In today's talk, I will be focusing on planar graphs, and I will start, and since planar graphs are sparse graphs, I will start with the bounded degree graph model, which was introduced by Goldreich and Ron in 2002. And in this model, we are assuming that we are given an undirected graph G with vertex set V and edge set V. And we assume the vertices are numbered from 1 to n. N is given to the algorithm. And we assume that the graph has a bounded maximum degree of B. We further assume that we can that we have access to the graph, so that for every vertex we can query for its ith neighbor, and we are either getting the ith neighbor or some special symbol that indicates that the ith neighbor does not exist. A graph property in this context is a set of graphs that is closed under isomorphism, and in property testing, we want to distinguish between graphs that satisfy a certain property and that are far away from the property. And therefore, we need the definition of epsilon far. And we say that a graph G is epsilon far from a property P if one has to modify more than epsilon dn edges to obtain a degree bounded graph with property P. Now, this definition of epsilon far always depends a little bit on the precise input model we are using. For example, in the dense graph model, one would have to modify more than epsilon with squared edges. And in general, the assumption is that your epsilon far, if you have to change an epsilon fraction of the object's description, to obtain an object that has the desired property. If a graph is not epsilon far from a property P, it is called epsilon close. Yeah, so the goal of property testing is to develop sampling algorithms that have this sublinear access to the input graph, and that are able to distinguish graphs that have the property from graphs that are epsilon far from the property. And now I'm going a little bit back in time to roughly 2006. And at that time, we knew that some basic properties are testable in the bounded degree graph model, things like connectivity, K-connectivity, and a few other things. And also, these are testable in constant time. So you have an algorithm that queries the graph in a constant number of places and can distinguish between the case that the graph is connected and the graph that is epsilon far from connected. And we also had algorithms for properties like bipartiteness, where we had a query complexity and a running time of roughly order of root of n. And we had a few of these results, but in the bounded degree graph model at that time, we didn't really know what are classes of testable properties. And at the same time, we already had a fairly good understanding of the dense graph model, where we could identify that there connections to the regularity lemma. And one had quite a good idea what properties are testable and what properties are not testable in constant time. But as I said, for the bounded degree graph model, we didn't know much. And yeah, then Arthur Jumai, Asaf Shapira, and myself, we started working on this, but we realized that we don't really have an idea to solve the general problem. And so what we did was like a standard approach in graph theory. If we cannot solve the problem for all graphs, then why don't we look at simpler classes of graphs? And our starting point was to consider planar graphs. And then we realized quickly that one thing that is very helpful in planar graphs is the planar separator theorem, which just tells you that if you have a planar graph, you can partition it by removing roughly a root of n vertices into two sets A and B, which are not connected. So C is the separator, and if you remove the set C, you are getting disconnected sets A and B. And if one applies the separator theorem repeatedly, recursively, then one can also partition every planar graph into connected components of size order 1 over delta squared by removing at most delta n vertices. And since we are considering bounded degree planar graphs, this is also, or this also implies that we can remove delta dn edges, namely the edges that are incident to the vertex separator, and also obtain in this way connected components of size 1 over delta squared. Now, this is something that can be very helpful in property testing. And in order to understand this, let's just look at a very simple example of testing 3 colorability in bounded degree planar graphs. And here, there's a simple observation. If a bounded degree planar graph is epsilon far from 3 colorable, then after removing delta dn edges for some delta, say, which is epsilon over 2, the resulting graph is still epsilon over 2 far from 3 colorable. That's just by definition of epsilon far. And but yeah, if we do this for the separator, I mean, if we apply the previous results with delta equals epsilon over 2, then this means that we can decompose the graph into many small connected components of size at most 1 over epsilon squared. And yeah, many of these connected components are not 3 colorable, simply because the resulting graph is still epsilon over 2 far from 3 colorable. Which means that we can design a very simple tester for 3 colorability in the following way. We sample some vertices uniformly at random, and the hope is just that one of these sample vertices lies in some of these connected components. And then for each sample vertex, we just do a BFS until a depth of 1 over epsilon squared in the original graph. And we check whether this neighborhood is 3 colorable. Now, if one of my sampling vertices lies in a connected component that is not 3 colorable, then this BFS will cover the whole connected component and potentially more vertices of the graph. But if we already have discovered a subgraph that is not 3 colorable, then we know that the graph is not 3 colorable. So when this neighborhood is 3 colorable, then that's fine. But if not, we have found proof that the graph is not 3 colorable, and we can reject. Otherwise, if all neighborhoods are 3 colorable, then we accept. And this, for the right choice of S, will give a constant time tester for 3 colorability in bounded degree graphs. And one can generalize this a bit, and one can show that all hereditary properties of planar graphs are testable in the bounded degree graph model, and one can also extend planar graphs to some bigger class of graphs. Then in the bounded degree graph model, there were a lot of further results that are kind of based on looking at separators in planar graphs. One of them is the paper by Beniamini, Schramm, and Shapira, who showed that every minor close property is constant time testable. And they were using that, that one can identify whether a graph has can be decomposed into small connected components by removing few edges. And once you have identified this, this can be used then to test, for example, planarity. Then Hasidim, Kellner, Yen, and Onak introduced partitioning oracles, which is a tool that allows you to get sublinear time access to such a partitioning of planar graphs. And there was a lot of follow-up work that improved the running times of these partitioning oracles, with a recent result by Kumar, Shehzadri, and Stollmann, who got the first polynomial time partitioning oracle for minor closed graphs. Ilan Newman and we showed that every hyperfinite property is testable in constant time, where hyperfinite also means that we have a partitioning into small connected components. And with Hendrik Fichtenberger and Pan Pen, I proved that every infinite testable property has an infinite hyperfinite subproperty. So hyperfiniteness, so this property of having a good separator into small connected components, turns out to be a very important part of property testing in the bounded degree graph model. There were also some recent results on obtaining faster testers for minor closed properties, and many more things. So that's all I wanted to say about the bounded degree graph model, because the main part of today's talk is about planar graphs, which where we don't have the guarantee that there's a bounded maximum degree. And this brings me to the sparse graph model introduced by Parnas and Ron. And in this model, this is a model for sparse graphs without a degree bound, and the algorithm in this model can query for the degree of a vertex and also query for the ith neighbor of a vertex. And a graph is epsilon far from a property if one has to modify more than epsilon m edges to obtain a graph with property P. And here, one natural assumption is to assume that the number of edges is at least linear in the number of vertices. In the sparse graph model, if I'm assuming constant average degree, there are also some known testability results like connectivity, K-connectivity, being Eulerian, diameter, also bipartiteness can be done in order of root of n time. Triangle freeness we can do in order of root of n query complexity, and a few more results, but not too many results we have. Then at some point I looked with Arthur, Jumai, Morteza Monemi-Sadeh, and Christoph Onak at this model, or at a slight variant of this model. So we were assuming that we can query for random vertices and query for random neighbors, which are things which we can do in the sparse graph model by Parnas and Ron. The reason why we were choosing this slightly different model is that in the sparse graph model, if we can query for vertex degrees, we are getting some information which we usually cannot get or it provides some information about the graph, which is not really a constant information because we know like how many neighbors we have. And this is particularly important if you want to prove lower bounds. Yeah, so since we are looking at planar graphs, we will just assume that the graph has set of n edges. So a graph with at most set of n edges is epsilon far from a property P. One has to modify more than epsilon times n edges to obtain a graph with property P. And this can be also written as just saying, or it's roughly the same as saying that one has to modify more than epsilon times the number of vertices edges. Okay, so this is about the model we are looking at. And again, it would be nice to make some general statements about the sparse graph model. So can we say something about the classes of properties which are testable in sparse graphs? But yeah, that's something that at least for us was out of reach. And so we took the same route again as we did for bounded degree graphs. And we just thought again, why not look at simpler classes of graphs? And we ask ourselves the question, which properties of planar graphs are testable in constant time? So now we have general planar graphs and not the degree bounded planar graphs. And of course, we can also again look at three colorability. And yeah, we were quite optimistic that one can easily prove, or well, maybe not super easily prove, but at some point prove that three colorability is constant time testable in planar graphs. But that's something that I still leave as an open question here. So this is, I think, a very nice question, but yeah, we haven't been able to solve this problem. And what we could solve is we could show that bipartiteness, so two colorability, is constant time testable. And in the following, I will sketch the main ideas of the proof here. Yeah, so let me start with some very brief overview. So the algorithm we were using, the algorithm performs random walks, and it simply rejects if it finds an odd length cycle, which means that the algorithm always accepts if the input graph is bipartite. So we just have to show that if G is epsilon far from bipartite, then the algorithm rejects. And yeah, in the first step, we prove that if a graph is epsilon far from bipartite, then it has a linear number. So I'm assuming epsilon to be constant. It has a linear number of edge disjoint odd cycles of constant length. And that's actually not very difficult to prove. So we can use an analog of the planar separator theorem. Now, planar separator theorem doesn't help us because the separator might now involve many edges. So we cannot argue that we just remove all the edges incident to the separating vertices. But there's a theorem by Klein, Plotkin, and Rao, who showed that one can always remove, say, epsilon n edges to decompose the graph into components of diameter, of constant diameter, where the diameter is actually the diameter in the original graph. So now if I apply this theorem with epsilon n over 2 edges, I can argue the same way as before. So we know that G originally is epsilon far from bipartite. This also implies that at least one of the resulting components is not bipartite. Let's call this component C. Now, what we can do is we can take an arbitrary vertex from this component C, and we perform a breadth first search in the original graph from this vertex from C. And we choose the depth of the BFS such that it covers the whole component C. And there we can use that the diameter in the original graph is constant. Now, since C, after the removal of these epsilon n over 2 edges is still not bipartite, we know that there must exist two vertices, U and V, which are connected by an edge and which are in the same level of the BFS tree, as otherwise C is bipartite. And so the union of the BFS tree and this edge results in an odd length cycle of constant length. And we can just remove the cycle and repeat the argument. And in this way, we can construct a linear number of edge disjoint cycles. So that's the first step of the proof. And then in the second step, and that's the main reduction. In the second step, we want to design a graph G star, which has the following two properties. So the first property is that if I'm doing a random walk of constant length on G star, and if this random walk finds an odd length cycle in G star with constant probability, then it also finds an odd length cycle in G with constant probability. So, and then we also show that, we also want to have the property that a random walk of constant length finds an odd length cycle in G star with constant probability. And the two things together imply that a random walk of constant length finds an odd length cycle in G with constant probability. And we can just improve the probability by repeating this process. And our starting point is to try to use G prime to be the union of the cycles found in the first step. So G prime is always a graph on vertex set V. And we start by just taking all the cycles that were found in the first step. And then we have to apply a number of additional processing steps to make sure that these properties are satisfied. So the first step is some sort of cleaning step, which essentially makes sure that every vertex either has degree 0 or a constant fraction of its degree in the original graph G. And also we want to have that sufficiently many cycles remain. And if we make sure that this is true, then this implies that the first property is true. So why is this the case? Because if I'm looking at a random walk of constant length, and if I know that a random walk finds an odd length cycle in G star with constant probability, then the probability of choosing the same cycle in G only differs by a constant, because at every step, constant fraction of the degree in G is also present in G star. So the probabilities of choosing the same edge only differ by some constant. And so this implies the first property. And this can be, so it's not very hard to show that one can process G star in such a way by just iteratively removing cycles that do not satisfy our assumption, and then just combine this with certain averaging argument. Now, the result of this processing could be a graph like this. And this graph is actually some graph which shows why the analysis fails, or why it is difficult, or at least for us, it was difficult to find an analysis. Because usually one might approach this problem by just fixing some cycle. And then maybe we want to argue that that with some probability, we find this fixed cycle with some good probability. But the issue is that there are graphs like this where if we fix a cycle, then the probability of finding exactly this cycle is very small. And so you should think of this graph as having as the orange vertices having many parallel cycles, so not just the 3 cycles here, but many more. And now if you look at this fat cycle, then of course it's difficult to argue that a random walk walks exactly along this cycle. Well, one can do it, but the probability will be very small because each of the orange vertices have a very high degree. And at the same time, it's not very hard to see that for this example graph, it is very easy to find an odd length cycle because you just have to walk around the graph once. So that's going to happen easily. So the question is just, how can we argue that this is always happening? And yeah, so we were using this example quite a lot to see whether approaches were working or not. And yeah, so then what we did in the next step is that we were looking at vertices of degree 2. And we were making the following simple observation that if a random walk starts at V and moves to W, then it will also with probability 1/2 reach the vertex U. And so from the point of a random walk, we could just replace the path VWU by a single edge VU. And this will only change the probabilities of random walks by some constant. And so we view this replacement as a contraction of V of W into, say, vertex V. And we also, since we want to discover odd length cycles, we also need to remember the parity of this path. Which means that in the end, we want to do the following thing. So we want to self-reduce our graph in a number of steps, such that the graph always becomes easier, and such that the random walk probabilities do not change a lot. And so here in the first step, we are taking these 3 vertices which are attached to the arrows, and we contract them into the single vertex here, which is now fat. We are remembering that we are now replacing paths of length 2 by a single edge, and that's why I colored the edge green. So just to remember the parity. And then we are getting a simpler graph with somewhat shorter cycles, and we can repeat this approach again here. And we just need to remember that the vertices now correspond to sets of vertices, and the edges now potentially correspond to parallel paths. But in principle, we can just simplify the graph more and more until at some point we reach a very simple graph, which just consists of a single vertex and a self loop. And of course, a random walk in this graph easily finds an odd length cycle because it just starts at the vertex and then follows the self loop. And now if we make sure that if we find a cycle, an odd length cycle in this graph, then we also find an odd length cycle in this graph. And that's the property we always want to maintain in our reduction. So if we find an odd length cycle here, we also find an odd length cycle here. If we find an odd length cycle in this graph, we find one here, and so on. And at some point when we move back the whole reduction, we also can argue that we find an odd length cycle in the original graph. But in every step of the reduction, we are losing some constants in the probabilities. So that's the main idea of the reduction we want to perform. And yeah, so we start with a graph that is a union of a set of cycles. we want to apply these contractions to paths of length 2 such that the length of every cycle in C gets reduced by at least 1. And such that if a random walk in the new contracted graph finds an odd length cycle, then it will also find an odd length cycle in G. There are lots of technicalities here, so we need to deal with weighted edges because they might represent parallel paths. We need to deal with weighted vertices because vertices after the reduction represent sets of vertices. We need to maintain parities of edges and so on, but I don't want to go into these details. So so how can we construct this new graph? Well, there's what one can show is that most cycles in G have a vertex of constant degree, and we just drop the other cycles. And then we remove further cycles to make sure that every cycle has a vertex of degree 2. Then we apply our cleaning lemma, which ensures that vertex degrees are either 0 or a fraction of the original vertex degree. And so this, again, one can do essentially by using some averaging arguments, at least if the graph is unweighted. Later on, we also have to do it for the weighted version, and that's a bit more complicated. So to put things together, we want to apply the self-reduction until every remaining cycle is a self-loop. Then, of course, self-loops are trivially detected by random walks. And we just have to argue that there are sufficiently many self-loops left, and that's what's taken care of by the reduction. And so this way we can show that bipartiteness in planar graphs can be tested with constant vary complexity. Now, an interesting question is to try to extend this approach to subgraph freeness. And here the point is that one can essentially view this previous approach as an algorithm to find subgraphs that are short odd-length cycles. And the question is whether we can extend this to more general subgraphs. And the challenge is that more general subgraphs will also have vertices of degree bigger than 2. And so we cannot use this argument of contracting paths anymore, but we have to extend it to something else. Essentially, we need to do two things. We need to replace a random walk by a random BFS of constant size. So we are always moving from one vertex to a constant number of neighbors randomly. And then from each of them, we are moving to constant number of neighbors and so on. And we also, in the analysis, need to introduce hyperedges to describe the random walk behavior. For example, if we want to contract a vertex of degree 3, then it is connected to 3 other vertices, and this we have to take care of by introducing hyperedges. But one can extend this previous approach to H subgraph freeness. That's something I proved with Arthur. So we showed that H subgraph freeness in planar graphs is constant time testable for some constant size subgraph H. And we also show that this is if and only if. So we showed that the graph property is testable in planar graphs if and only if it can be reduced to testing for a finite set of forbidden subgraphs where this set is potentially different for every n. So it's a weak notion of testability here. To conclude, we have seen that property testing without degree bound is challenging even in, well, simpler classes of graphs like planar graphs. And in particular, this requires a good understanding of random walks and random walk-like explorations. And so I'm concluding here with a number of open problems that I find very interesting. So I already said that we still don't know whether 3 colorability is constant time testable in planar graphs. I think that's a very nice problem to work on. We also don't know what it means to test for forbidden subgraphs. This, in particular, is it possible to prove that all minor closed properties of planar graphs are testable in constant time? And then one can also think about planarity testing in the sparse graph model. So what is the complexity of planarity testing? Is planarity testable with sublinear query complexity in the sparse graph model? So there's no hope for a constant query complexity tester here, because you could simply have a clique of root of n vertices, and finding this clique takes root of n time. And so testing planarity requires at least root of n time. But then one can also ask whether random edge queries help in planarity testing, because random edge queries would allow to quickly determine whether a graph has such a small clique. And so maybe one can show that using random edge queries, planarity testing is possible in constant time in the sparse graph model. Yeah, and that's all I wanted to say. Thank you.